nanohub.org.
All right. So, good afternoon, everyone. What I'd like to go over is a sort of an introduction lecture, which I would call the formation of band structure, and then some RTDs, and then we'll go into NanoHub and we'll play with a couple of tools where you can sort of run your own what-if experiments that sort of should duplicate some of the stuff we're doing. So what I want to do is look at some first analytical solutions to toy problems and then numerical solutions. And the tool that we use first is this piecewise constant barrier tool. And you might have heard of a scattering matrix approach. Who has not heard of a scattering matrix approach? Okay, so okay, a couple of hands, all right. So the idea is that you take a heterostructure like this and you shine, say, a wave into it from the left, and you shine a wave in from the right, and you try to figure out how much is transmitting and how much is reflecting. Okay? And that is similar to systems theory, where you can do this with classical systems. You can also do that with quantum mechanical systems. And the idea is really that in the middle, no particles are lost. And typically what you do is you inject, say, from the left only with A equal to 1. And you set the incident wave on the right to 0. And you try to figure out what makes it through and what comes back. All right? That's sort of the global picture. And you can do that sort of with for a single barrier, for example. You might say, I have an incident wave here on the left, a reflected wave B on the right, and I'm interested in what is being transmitted. So you can do this in a sense where you say, okay, I want to have an expression for my wave here on the left side. I'm going to write it as an e to the ikx plus b to the minus ikx. So a forward and a reverse propagating wave, right? That's sort of just a simple ansatz of what this system would allow. And then you say, well, I'm in the middle of the barrier here and I'm injecting at an energy below the band edge. All I can have is a wave that is decaying down forward and a wave that is decaying or increasing exponentially to the other side, right? So you have an e to the minus kappa x and an e to the plus kappa x, okay? And then on the other side, you might have again, a forward and a reverse propagating wave, okay? And basically, you start with this ansatz saying, those are the fundamental solutions that must be allowed. And what you then have to do is sort of match the wave function here at these interfaces, okay? And by these matching conditions, you can do that. So you basically say that the wave function has to be continuous at the interface and the derivative has to be continuous at the interface, right? And you do that for the two interfaces and you get 4 equations, all right? So that you can write into a matrix like that, where really you start to write down a matrix of coefficients, like with A and B, and they're related to C and D are related to E and F, right? So at each interface, you relate input and output, so to speak. And what you can do is you can then generalize that, right? So A and B are related through a matrix M1 to C and D, and then C and D are related through a matrix M2 to E and F. And that is really one big matrix M that relates E and F to A and B. So in a sense, that is called a transfer matrix method, okay? So you can string things together quite long. So basically, you can get to a system representation with a system matrix like that, and if you string them together in a row, you multiply these transfer matrices. So this looks conceptually very simple, and it's analytically pleasing. It's a numerical bear, okay? I'm not going to do that here. So what you need out of this, in a sense, is the ratio of what comes out at the other end divided over what went in on the left end, okay? And you take the magnitude square, and that is really one of the matrix elements, and that's the transmission coefficient. Okay? So if you have not seen this before, sort of standard lectures, there's actually lectures on this on the Nano Hub. I'll invite you to go there. There's a couple of, so you can actually evaluate this whole matrix explicitly. And if you're in the regime where you inject under the barrier height, you have a hyperbolic sine function that is in there. If your energy is above, you actually have a real sine function in there. And notice that has, in those sine functions, you have K2 over L or gamma in L, okay? So that barrier width L is showing up in that analytical expression, okay? And above the barrier, it actually shows up in a sine function. It's almost like a bound state, but it's a quasi-bound state that sits above the barrier. And it sees the perturbation of interface to interface even above the barrier. Okay? So that comes out analytically, just like that. You can make some approximations when the barriers are high, etc. Then you basically get exponential type functions, but that's okay. So that's what I've shown in the morning. So you can transmit through a barrier. It's exponential decay under the barrier, but on top of the barrier, it's not exactly one, and there's a sort of a quasi-bound state, okay, that exists. And at that quasi-bound state, the reflection is going away and transmission is going to 1, which means above the barrier, the reflection is not exactly 0, okay? There's still electron waves are going to be reflected above the barrier. All right. So notice here that formula again. If you make that barrier thicker and thicker, you actually pack in more states that are closer spaced. Okay? It's like a quantum well, you make it wider, you pack in more states. There's less spacing. So you actually pick up more of these quasi-bound states above the barrier, which is kind of surprising, right? So the key summary is, again, quantum wave function can tunnel through these barriers. Tunnel is reduced with barrier height and width, and the transmission above the barrier is not unity, right? Those are the key messages to take away. So that was analytical, right? And I just showed you a numerical example at the end. It gets really tedious to do that, by hand, right? That's why you have computers. And so I'm going to show you some numerical solutions. You can do this, by the way, this analytical stuff literally as a homework assignment, double barrier. If you like, you either do it in Mathematica, it does it for you, or you push paper and pencil around. That's cool too. So here you can consider now a double barrier structure, and you can do the same thing, and you do basically 4 transfer matrices, and you do the same principle, and you basically get a bound state that sits in the middle between a double barrier, and you even have a quasi-bound state that sits above the barrier. And if you make the barriers taller, you can bind these states closer. The tall barriers have sharper resonances. If you make the barriers thicker, you make the resonances definitely sharper. And again, that is a reminder that the electron rattles around there longer, so to speak. Its lifetime is longer. So the broadening is less, right? It's less broadened. You can think of it as a good Q cavity, if that means something to you, or a very well-defined resonator, if that means something to you, right? You can also think of this whole thing as a sort of a particle in a box, right? I mean, you're confining a particle, and here's sort of a ground state, here's an excited state, this is a density of states plot, and you can ask yourself, how does that relate to a particle in a box, right? Because that you can compute easily. Everybody here can compute a particle in a box. Here's Schrödinger's equation, right? You set the potential to infinity on below 0 and above L. And everybody knows what the eigenstates of these, of this Schrödinger equation is in the particle in the box. And you know that the eigenenergies are spread over n square, right? And you fit in exactly 1 lobe and then 2 lobes and 3 lobes, and they spread out as a square law, right? So you know how to do that. I'm not telling you anything new. The question now is, how does that relate to what we do. So we might represent these wave functions as with straight lines. And here's what this PCPBT tool can do for you, right? In number one, it can take this RTD-like structure and identify where the transmission peaks might be, right? Where the true eigenenergies are. And it can also compute for you a particle in a box system, right? Well, you can do it on paper, but that tool puts it next to each other on the screen, right? And what you see is that in green, those are the true particle in a box states. And in red, those are the bound states. And what you find is that, so here's a pair, 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 and here you start losing track of the pair. You actually found that the open system has resonances that are slightly lower. It's a concept of a damped resonator, right? The particles can get out. They are not so strongly confined, right? So you can actually show that analytically or now with numerics that is like a particle in a box, but the eigenstates are a little bit modified, and they're modified by an open system. All right? So this openness is actually very important. It's not only that electrons can make it through, that's it. No, the eigenstates of the system are actually modified by the existence of an open boundary condition. Okay? So think about that again. It's not just taking an ideal system, figuring out where the states are, and regardless on how you create these contacts, those are the energies where the electrons are going to sit. The open boundary will modify the quantum system on the inside. Okay? That is what that means. Right? It's a very fundamental statement. All right. We made really thick barriers, 10 nanometers, and really tall barriers, and a really wide well. Okay? So really big barriers, so really strongly confined, and we see that the spacing is okay. And it starts to deviate for the higher energies, right? But if I actually go in and do something more reasonable, like I take a thinner barrier, this is actually a thick one still, 8 nanometers, and make them shorter to 250 milli-electron volt, and even a wide well of 10 nanometers, there the difference is even worse. Okay? Yes? Sure.
So at very high energies, again, the difference between the red and green lines.
Right. Yeah. Well, green is the open system, red is the closed system. Okay? And notice that these build a pool, these build a pool, these belong together, and this red belongs to this green. Right? And you lost track of that. You think they belong together, but they're not. This green belongs to this red. Right? So overall, the energies come down in the open system. Now, if you now take a more realistic system, where the barriers are not that tall and not that fat, then the eigenstates come down even further. So you sort of see how the openness of the system dramatically has modified your quantum system. Okay? So just doing a particle in a box might give you some ideas, but not quite. All right? So, so we have these eigenstates here. What we can do now is also look at try to ask ourselves, why is there such a big difference? Well, in a closed system, the barriers here are infinite, right? The wave function is not allowed in there. In an open system, the wave function is actually allowed to penetrate into the barrier. So if you are in an excited state, the higher excited the state is, the more the wave functions like to penetrate in the barriers, right? So the openness, in a sense, makes the barriers a little bit transparent, and therefore the states are deviating from the closed box. All right. So the key summary on the double barrier structures, there can be unity transmission below the barrier height. That's called resonant tunneling. And they can be associated with a quasi-bound state. And there's certain effects on barrier heights and widths we had discussed before. So now we're going to make this a little bit more complicated. We're going to tunnel through N barriers. Okay? And you can duplicate this then on the NanoHub and play with it and get some ideas. So here's a double barrier device, and here's a transmission coefficient, all right? And I chose a pretty shallow barrier height, a pretty wide well, and a pretty thin barrier. Yes?
I mean, when you calculate this using 3D NEMO model, in this
Yeah.
case, do you need to pass the barrier potential as an input? Barrier potential profile.
Well, so this is an input parameter.
So my question is there any difference that if you pass just the well potential and if you pass the barrier potential and the well potential?
Oh yeah, we can play with that. We have a tool, it's not in this tool, where you sort of have you could have a soft barrier and then an infinite barrier, for example, right? And then you can probe the dependence on barrier penetration. You can play with that. Is that what you're asking?
No, what I'm asking is there a difference if you just pass the well potential, just that line, the well?
I don't know what you mean. Maybe you want to go on the drawing board. And then, well, right here. I'm not giving you my gun.
So, if you pass just this potential,
yeah,
or if you pass the whole thing.
Well, we can play with that. So let's play with that. Okay? I think there will be. All right? So, double barrier structure. Now I'm going to do the following. I'm going to add a barrier. All right? So now you have two quantum wells, and you have two states that are sitting in it. All right? And you have a transmission that goes to one at these two energies. All right? So think of this as a hydrogen atom with one s orbital. Okay? Now you're going to bring closer a second hydrogen atom. Those s orbitals are going to talk to each other. And there's a so-called bonding and anti-bonding state. Here we go. There's a bonding and anti-bonding state. Okay? And they talk to each other. And electrons are allowed to pass through either one of these resonance energies at a perfect one. All right, now check this out. We'll add a fourth barrier. We will have three wells. That's getting three states together. They talk to each other. And you get a transmission of perfect one. Yes?
Can you map this problem to chronic?
Good question. We'll get to that. That's exactly the point of this lecture. All right. So now we have three wells, three transmission peaks. Take 4. Take 5. Take 6. And you notice that this pass here, right? This sort of pass filter here is getting sharper and sharper. So if you've ever calculated bandpass filters and strung them in series, that's what you got, right? You're building a bandpass filter. And you're basically tuning it with the width of your resonances. That's like an RC circuit, LC circuit, okay? All right, now 7, now 8, now 9, 19, 29, 39. 49. All right? So for each of these wells, you pick up a little bit of a resonance. But you pick up a band. Yes?
Is the energy spacing between the resonance?
That's a great question. The question is, what is the energy spacing between those, right? Give me about 3 slides. Okay? So here's the animation of this thing. So notice that this bandpass filter is getting sharper and sharper. And it starts out from being pretty broad, right? 1 or 2 resonances, pretty broad, and you make it narrower and narrower, right? So you just eyeball for yourself. When do you think this is a band? Right? Right? Is it 6, 7, 8, 10, 20, right? At some point, you decide for yourself what is a band, what is it, when is it a band? So you might say this is a goofy exercise, but think about this. You have a silicon structure and you put a layer down of silicon dioxide, for example. Silicon dioxide is or you have a heterostructure of, say, gallium arsenide and indium arsenide. After how many atoms of gallium arsenide does it actually make sense to talk about a band structure, right? It's somewhere between 6 to 10, right? If that concept wouldn't make any sense, all our calculations that we do wouldn't make any sense, right? We can scale devices down. We talk about the band edge, right? Here you see a band edge emerge, right? This is a band edge. This is a conduction band edge, and this is the top of the band. That starts to emerge after 6, 7 atoms, right? This is a quantum well, but this could have been just as well atoms, right? That's the translation I want you to make. All right.
Talking about the top of the band, we never talked about the top of the band.
Oh, we will now. So going back to the top of the band and what's the location of these resonances, right? So I can keep track of this resonance peak right here, and here's a dot, okay? So for each well, I should get a dot, right? So, right, one state, one well, one transmission peak, one state, right? So I'm going to plot the states on, this is just an occurrence, and this is the energy, or where they show up, right? I have 1, I have 2, I have 3, 4, 5, 6, 7, 8, 9, 2. There's your band. Okay? So, when I was a student and I was tortured with a chronic penny model, the first thing I had to wrap my head around was a periodic boundary condition on a single unit cell. And that's a nice mathematical exercise, but I actually had no intuitive feeling of what that meant. This, to me, is a very intuitive way of thinking about stringing atoms together and figuring out at which point do they actually form a band. And then the leap to say, well, if I had many of these, that these might be almost continuous, depending on how many atoms you have in this thing, is actually more a natural leap. So I like this way of presenting band structure much better than a chronic penny model. But, you know, since we have a bunch of people that like chronic penny models, you can actually overlay this with a chronic penny model, and there's an exercise on the NanoHub on PCPBT where you can take the two codes, take the same barriers and same wells, and you can get the same result, overlap it almost perfectly. Okay? All right. So here's this animation thereof. I think we got the message, right? We are basically filling in states depending on the size of your unit cell. Okay? Yes?
So I noticed that the barrier height is about 0.1 dB.
Yeah.
Exclusively, but for zero case, like silicon is over 0.
Well, so this is my toy example, right? Of 100 millectron volt barrier, right? So now I'm gonna ask, what was that? Sorry.
What is the problem in the expected difference?
Oh. Yeah. So this is distance. These are basically the barriers, right? This is transmission coefficient, and this is occurrence, right? Meaning number of states that have shown up, right? And then you can normalize that over some unit cell, and that's your k-vector. K-vectors are no different, right? You're counting the number of states in a space, in a reciprocal space. That's it. Okay? Well, you can interpret it as a transmission. I can also interpret it as an eigenstate that has a spatial extent. Right? It's a particle in a box. I can plot a density of states. I might have it in this presentation, actually. So now I'm going to make this barrier taller, right? So this is the old example on the top. Now I'm going to make the barrier taller by 400 millectron volts, right? So now with 400 millectron volt barriers, I should see at least 2 states. And look, there's 2 bands forming, and the lower band is actually pretty narrow in energy, and the upper band is pretty broad. Just like in a real band structure, right? You're sitting closer to the core, the electrons have a very heavy mass, they don't propagate very far, and the higher you go in energy, the more spread out your energy states are. Falls out for free. So if you have 2 states per well, you have 2 bands, right? Yes?
When you go to the meaning like 50 barriers,
Yeah.
does your transmission coefficient goes to 1 always?
Yes. Why don't you believe me? It's numerical a real pain because you got to find these guys, right? You got to have, I mean, these plots here, right? They're resolved by like 50,000 points. You can't see it, but you got to find it numerically. But it goes to 1. But you can sort of see by the background here, right? It doesn't go to 1 everywhere, right? But on that resonance energy, it goes to 1. All right. So you get the picture, right? If I make the barriers tall enough and I make the well a little wider, I can confine 3 states. And you see a very heavy band, right? Down here. The mass is, I mean, there's almost no bending. And then the next one bends further and the next one bends further, right? So you go from, on the core, you're pretty heavy. The electrons don't get to move so freely. And to the top, they start to move pretty freely. Okay? So here's the animation of that. So the bottom line here is really each quasi-bound state will give rise to a resonance in a well, and that's the number of barriers minus 1. The degeneracy is lifted because of the interaction between these states, and a cosine-like band formed as the number of wells and barriers is increased, and each state per well forms a band. Right, so here's 1 state, 2 states, 3 states, so we have 3 bands that are starting to form. Okay? And the lower bands have a smaller slope, that means they have a heavier mass. All right.